Well, we are discussing periodic classification. At every point of time, I would like to remind you, this chapter is absolutely important because the one who is really good at periodic classification is actually good at chemistry. Because the entire chemistry that is outside has been put in the periodic table. You must understand that. So it's not a trivial case where all your elements are, randomly placed everywhere in the periodic table in rows and columns. It is not the case. There are rules, there are schemes, there are principles which drive the entire periodic table you must understand. And I would love to remind you every point of time that you have infinite number of shells in the periodic table. Infinite number of periods rather. And each period is a shell, is regarded as a shell, which is designated by a principal quantum number. So n values start from 1 and go for infinity. So you can expect infinite number of even periods in the periodic table, you must understand. Now if that is the case, if you look into the periodic table in your textbooks, you will find that the 7th period itself is incomplete, right? So it leaves a scope for you to check out some more elements that are left out, and you can have a place here in the periodic table already fixed. You must understand that. So if any element is discovered later, 20, 30 years from now, its position is absolutely fixed in the periodic table, you must understand. Right? So that is the scope of the periodic table. So it's not trivial. It's not a child's play where you are given 120 odd elements and you are supposed to place them in rows and columns. It is not that case. You must understand. It rather stimulates research. This is the point which I would like to remind you every time I take up a subtopic. Right? That's number one. Number two, which I would like to remind you, is there are some properties which repeat itself at regular intervals in the periodic table. Right? And those properties, I call them to be periodic properties, you must understand. And what is very strange is this entire periodic properties are basically functions of sizes. So if they are functions of sizes, the modern periodic table or the modern periodic law is a function of atomic size. So if someone is asking you what is the basic difference between 120, 130 elements that are present in the periodic table, then I would like to say it is all about size. So the mode of activity, that's nothing but your physical and chemical properties, which these elements exhibit are basically functions of atomic size, you must understand. You must understand that, right? So the prime is atomic radii. Why lithium has a different set of properties, why sodium has a different set of properties, why scandium has a different set of properties, why lanthanides have a different set of properties. It's all about size, right? Even if you look into some of the periodic properties which we have discussed, electropositivity, electronegativity, electron affinity, or even metallic nature, or reducing nature, or oxidizing power, all these are basically nothing but functions of atomic size. You must understand that. Right? Even Lanthanoid contraction, which is very, very important subtopic which I was dealing in last few classes. And mind you, this Lanthanoid contraction applications are questions which are asked in JEE advanced exam. Please understand that. It's asked in JEE advanced exam as well as the other exams, you must understand. So you can bank on this subtopic, right? If I can brief you before I actually take some more applications of Lanthanoid contraction, well, understand what is Lanthanoid contraction is. Basically, it's a phenomena which you see it in the F block. And if you normally look into the periodic table, the demography of the periodic table, it basically has S block to your extreme left, P block to your extreme right, and in between you have D block. And from the main frame of this 18 groups, that is 2 plus 6 is 8, and in between you have 10. So 10 plus 6 is 16 plus 2, 18. Out of this 18, this forms the main frame of the periodic table. And out from the main frame is the F block, which is placed as two series at the bottom, the 4F series and the 5F series. And this Lanthanoid contraction is a phenomena where it is a reality which we actually encounter in the 4F series, which is otherwise called lanthanoid series, which are removed from the main frame of the periodic table to maintain the decorum of the periodic table. You must understand that, right? So What is Lanthanoid contraction? Is a consequence. In fact, understand that it's a consequence of shielding effect. Shielding effect. So if this can be considered as one of the applications of shielding effect, you must understand, right? And you might be having several applications of shielding effect, but this one seemed to be significant because it affects several properties of these rare earth elements. That's nothing but lanthanides. You must understand that, right? If that is the case, then what basically shielding effect is, if you can recollect, if in between a nucleus and the outermost shell, if in between a nucleus and the outermost shell, if the number of shells increase, the number of electrons are occupying sp.df, then the nuclear force of attraction, that is the resultant nuclear force of attraction that will be falling on the outermost shell, basically decreases. You must understand. So if the number, I'm telling you it's number, if the number of shells in between the nucleus and the outermost shell go on increasing, then the nuclear force of attraction that falls on the outermost shell basically decreases. Then what happens? The outermost shell is basically relaxing. Then the size actually increases, you must understand. So basically understand that greater is the shielding, more is what? Atomic radii or the atomic size, you must understand, because the outermost shell goes into a relaxation mode, thereby the size would be increasing. So one of the direct consequence for increase of sizes in a group is of course what? Shielding effect, you must understand. Is of course what? Shielding effect. That's why if you recollect, in any group, if you take from 1 to 18, you take any groups, right? The size increase which you actually see at the top, overall the size will be increasing from top to bottom. That's no doubt in the 18 groups. But the way it increases at the top would not be the same as you go down the bottom 3 elements. The top 3 elements, I think the way the atomic size increases is completely different from the way the atomic size actually increases for the last 3 elements. So it all depends on the bulk of the electrons being added to S, P, D, F. The S and P being a very good shielders, and D and F being a bad shielders, you must understand. Now what do you mean by bad shielders? S, if the bulk of the electrons are added to S, then S is symmetrical about the nucleus and it's covering the nucleus in a very non-directional mode. Whereas P has some angular density, angular electron density, you must understand. D is also having an angular density of electrons. So the shielding effect of S, which is symmetrical around the nucleus, right, is shielding more compared to P, compared to D, and the worst is F. And the worst is basically what? F. Because we do not know the shape of F orbitals. It is an 8-fold degenerate orbitals with having a peculiar diffused shapes. When I say having a peculiar diffused shapes, indicating that we don't know the exact shape of what? F orbital at all, and we consider them the F orbital having some pores in it, thereby the nuclear force of attraction penetrates through the pores and falls on the outermost shell. Thereby the outermost shell is basically pulled towards the nucleus and the size decreases. Right? So understand, S is a better shielder than P. P is a better shielder compared to D. D is a better shielder compared to F. That is how the trend of, right, the shielding effect is. Right? So if that is the case, then let us take up the F case. The F case, because after all, lanthanides belong to what? The F block. F block. So if you look into this lanthanides, this lanthanide contraction, basically what I'm speaking is a direct consequence, of shielding effect of F subshell. It's a direct consequence of the shielding effect of the F subshell. Now what is the consequence? Because F has a peculiar diffused shapes, I think the nuclear force of attraction is actually basically penetrating through the F and thereby falling on the outermost shell, thereby decreasing in size. So basically, why direct consequence of F subshell is F is a very poor shielder, you must understand. And this is has a poor shielding effect, you must understand this, right? So lanthanoid contraction is a direct consequence of the shielding effect of the F subshell, you must understand. Now where do we find these lanthanides? Are they D block or F block? What is this? Then observe, just a recollect of what I said. If you consider the 6th period, this is the 6th period in the periodic table. You have 7 periods and we are stopping at the 6th period, right? In 6th period, you have an element called lanthanum. This is lanthanum, which is 57, right? And it belongs to D block. This belongs to the D block, you must understand. Technically speaking, it is also put in F block because of properties, but if you consider electronic configurations, I think you don't have any electron in the F orbital of lanthanum. So technically, we call this to be a D block element based on electronic configuration, right? So this is lanthanum, and immediately you are supposed to get next element to be 58, which is not there, and it goes to 72, right? And this is hafnium, right? And you have here missing elements from 58 to 71. That is cerium to lutetium. You must understand. Cerium to what? Lutetium. They also belong to 6th period. So that might be a question. Lanthanides belong to which period is a question. That is, of course, they belong to what? 6th period, but they are not put in the main frame of the periodic table. Rather, they are pulled out from the main frame and put at the bottom. You must understand. This is cerium to what? Lutetium. So they belong to what? 6th period. Here, the 4F subshell is being filled. You must understand. Here, the 4F subshell is being filled. How it is being filled? Start from cerium. It is 4F1, 4F2, 4F3, 4F4, 4F10, 4F11, 12, 13, 14. It is filled down and then they climb up again at the 72. This is 71, the 4F is filled. You climb up here 72. So if you have a closer look at the periodic table in your textbooks, you will find that after 57, it is a straight jump to 72. You must understand. It is a straight jump to what? 72. And then the missing elements are nothing but the 14 elements which are placed put at the bottom. That is 4F subseries. And the F block, as I said, F subshell is a poor shielder and it can't what? Shield the electrons when you take one stride. That means if you're walking from left to right in lanthanides, if you walk from cerium to what? Lutetium. If you look into this, this is the nucleus of the cerium. If you walk one stride, 59, 60, 61, 62, 63, 64, the nuclear size is increasing. The nuclear size is increasing. So the nuclear force of attraction is also increasing. You must understand. As you move from left to right in lanthanides, the nuclear size is increasing, so you can expect nuclear force of attraction is increasing. But what is happening here, the electrons are added to the F subshell in between this is the ultimate shell and this is the penultimate shell, and you have here F subshell. Now the nuclear size is increasing and this fellow is unable to shield it because of poor shielding effect, and they penetrate through this and falls on the ultimate shell. So whenever I take one stride, the outermost shell is pulled inwards. If I take one more stride, the outermost shell is pulled inwards. If I take one more stride, the outermost shell is pulled inwards, resulting in a contraction. And on an average, if you actually see, the lanthanoid contraction is on an average, if you see, it is around 0.2 angstrom units, you must understand, which is significant as far as the dimensions of the atom is concerned. You must understand this. So on left to right in lanthanides, due to the poor shielding effect of F subshell, the force of attraction is penetrating and falling on the ultimate shell, resulting in contraction, which is lanthanoid contraction. And remember, this is significant because the average is coming to 1/5 of a angstrom unit, so which is very much as far as comparing into the relative dimensions of the atom. You must understand that, right? If this is the case, then this was told to you earlier also, but what are the various consequences of lanthanoid contraction, let us take a few more things. One of the direct consequence is how lanthanoid contraction affects basic nature of hydroxides. Remember that. And I wanted to draw the attention of everyone because this is 100% sure in exam. This is 100% sure in exam. Please understand that you can bank on it. How does the basic nature of hydroxides vary in lanthanides? That's from cerium, or take the case of lanthanum, to lutetium. How does it vary? So you need to tell basic nature trend from lanthanum to lutetium. From lanthanum to what? Lutetium, we need to tell the basic nature of hydroxides. How do we do this? Now basic nature of hydroxides means I'm speaking of lanthanum trihydroxide, and this is lutetium trihydroxide. You must understand, because the most common oxidation state what we find in lanthanides is +3, right? So you will be given hydroxides of lanthanum, cerium hydroxide, lutetium hydroxide, and all the hydroxides of the F block, and we need to tell which hydroxide is more basic and the trend which we observe in the lanthanides. That is one of the questions which is asked in exam, and this is 100% sure, right? To understand this, we should know the concept of polarization. So I draw the attention of everyone here, right? Watch carefully here. Watch. If you actually recollect Farjan's rules. Recollect Farjan's rules, right? Farjan's rules. Well, why are Farjan's rules told? Because where do we actually apply Farjan's rules? You must understand, right? And we will apply Farjan's rules to judge covalent nature in metals. Please understand that. Normally, metals are what? Metallic compounds are ionic. But to judge some percentage of covalent character even in ionic compounds, you please understand that. A bond between a metal and a non-metal is essentially ionic. But is it 100% ionic, 80% ionic, 20% ionic? Or how much is the percentage of covalent character in it is judged on the basis of what? Farjan's rules. You must understand if you recollect. Even in lanthanides, if you say this is a metal and the hydroxide is a non-metal. Lanthanides are supermetals rather. And hydroxides are what? Non-metals. And a bond between a metal and a non-metal is essentially what? Ionic. And what I'm trying to tell is to the percentage of covalent character, if we can judge in these hydroxides of the lanthanides, then we can judge the basic nature. Then we can actually judge the basic nature, you must understand. Right? If this is the case, then understand what is Farjan telling. He says, and I would like to quote, smaller the cation, smaller the metallic ion, smaller the cation, right, has more covalent character, mind you. Smaller the cations, recollect Farjan, he says, smaller the cation, mind you, smaller the cation, more is covalent character. More is what? Covalent character. When you say more is covalent character, then you have more non-metallic nature. Must understand. So more is covalent character, less is what? Less is what? The basic nature. You must understand, less is basic nature. So what Fajan is telling, if you wanted to judge the basic nature, then you must look into the size of the cation. Smaller the cationic size, more is covalent character, and less is what? Basic nature. That's what he says. That's what he says. Well, if you want me to explain more detailedly, so then have a look here. Watch carefully here. Watch carefully here. This is the sequence which we are supposed to follow. Look into this sequence. Look into this sequence. What are we doing? What are we doing? What are we doing? We are actually judging basic nature. We are basically judging the basic nature in lanthanoids. In lanthanoids. Basic nature in what? Lanthanoids. In fact, basic nature of hydroxides. In lanthanoids, that is from lanthanum to lutetium, that is 57 to 71. Please understand that. That's what we are doing. First, what we are doing, let us be clear. We wanted to judge the basic nature of hydroxides, trihydroxides rather, because lanthanum will show +3 oxidation state. People who are preparing for the advanced level IIT JEE should listen to me carefully. This is an advanced JEE question. So I draw your attention, please. Please understand that we are judging the basic nature in lanthanides, that is lanthanum to what? Lutetium. And remember and recollect, we know metals are bases. Metals are bases. If metals are bases, then good metals are actually good bases. If metals are basic, then good metals are more basic. If this is the case, good metals have big sizes. Good metals have big sizes. So what is a great metal in the periodic table? If you ask me, those metals are placed to the extreme left bottom of the periodic table. That is alkali metals. That's why we got the name alkali. And the left side people are the people who have the biggest sizes. And left to size, the size decreases. You must understand that, right? If that is the case, we know metals are bases. Look into the synonymous statements. Metals are bases. Good metals are good bases. Good metals are those which have big sizes. So basically I can simply say metallic character is a function of size. In fact, metallic character is directly proportional to the size. If metallic character is directly proportional to size, and metallic character directly proportional to basic nature, because all good metals are good bases. I say good is good, not good is bad. Good metals are good bases. So there is a direct relation. So metallic character is directly proportional to size. Metallic character is directly proportional to basic nature. It implies that basic nature is also proportional to the size, you must understand. Basic nature is also directly proportional to the size. So 2 questions I can ask. 3 questions. First, where are the big size elements in the periodic table? Left side. Big size metals are, where are they in the periodic table? To the left side. Where are good bases in the periodic table? To the left side. So the size, metallic nature, basic nature, are all 3 are what? Directly proportional, you can see. Basic nature proportional to size. Metallic, I can combine and write. Metallic character directly proportional to basic nature, which is proportional to the size. Must understand. It's proportional to the size. Same is even told by Fazen. What Fazen is telling, smaller the size, more is covalent character. So less is what? Basic nature. Less is what? Metallic nature. Less metallic nature, less basic nature, less size. That is what even Fazen is telling. You must understand that. Right? If this is the case, then look into this. If this is the case, if you say basic nature directly proportional to the size, right? Then we know size contraction in lanthanides. We have size contraction in lanthanides. That is, size decreases from lanthanum to lutetium. You must understand, the size goes on decreasing. You must understand. If that is the case, then basic nature of lanthanum trihydroxides, size decreases. So the biggest size is possessed by what? Biggest size is possessed by what? Lanthanum, right? Biggest size is possessed by what? Lanthanum. You can see here, size is more, basic nature is more. Size is less, then I think the basic nature is less. You must understand, right? So if you wanted to write and compare basic nature of, first of all, if I can write the size of lanthanum for you, let us compare lanthanum and lutetium. Let us compare this. We know size contraction happens in lanthanides. So I can simply say the size of lanthanum plus 3 is rather greater than lutetium plus 3. If you wanted to compare the lanthanum, that is the first element in the lanthanides, with what? Lutetium, which is the last one. I think since you have contraction in sizes, the size of lanthanum plus 3 is greater than lutetium plus 3. So I can simply say metallic nature of lanthanum plus 3 is greater than lutetium plus 3. That is the metallic nature. And if you wanted to go for basic nature, then I would like to say lanthanum trihydroxide is a better base compared to what? Lutetium trihydroxide. You must understand, because the size is directly proportional to this, metallic nature is not. Right. So basic nature, understand, simply speaking, forget about all this. Look into the sizes. See, in the periodic table, whatever the trends are, that is even applicable for what? Lanthanides, you must understand. Biggest sizes, you are placed to the extreme left. More size, more metallic nature. So good metals are placed to the extreme left. More metallic nature, more is the basic nature. That's what I'm trying to tell. In lanthanide contraction, you have a size decrease from lanthanum to lutetium. So lanthanum is a bigger element compared to what? Lutetium. So metallic nature, I think lanthanum is a better metal compared to what? Lutetium. And remember, basic nature will be also following the same order, and plus 3 oxidation states seem to be most common among all this. Right? If that is the case, then let us put all the things at one place, the lanthanide contraction properties. Observe here. Before I go there, I wanted to even discuss one more property, that is this. Watch carefully here. If I can list it out, all the properties to you, watch carefully. Watch. Please watch. Consequences of lanthanide contraction. consequences of Lanthanoid contraction. What are the consequences of Lanthanoid contraction? One, zirconium and hafnium have similar radii. They have similar radii. And let me tell you that zirconium is the 5th period element and the hafnium, this is the 6th period element. Corresponding zirconium and hafnium are one above the other and their placements are somewhat like this. This is hafnium, this is zirconium, and this is the 6th period, this is the 5th period. Corresponding elements. Corresponding elements. If you look into the periodic table, you will get to know. And what I am telling, if you look into the ionic radii of zirconium plus 3 and hafnium plus 3, right? The ionic radii of this, ionic radii, this is 83 picometers and this is 84 picometers. So you can see the ionic radii hardly changing for zirconium and hafnium. Right? You have zirconium and hafnium having a similar radii because of Lanthanoid contraction, which I was explaining it to you detailedly. So people who are writing the advanced level JEE exam, listen to me carefully. Right? So you have what? Similar radii. And the supplementary thing, the supplementary consequence of having zirconium and hafnium having similar radii, I can simply say zirconium, hafnium, right, are seen together. In fact, you understand the supplementary consequences. The other consequence is the hafnium will be an impurity in zirconium. You must understand, because zirconium and hafnium almost form a homogeneous mixture. When people form homogeneous mixture, it's an indicative of similar sizes. Not everyone will form homogeneous mixture. A 5 feet fellow cannot form a homogeneous mixture with a 7 feet fellow. All 5 feet, fine. You must understand. So due to similar radii, zirconium and hafnium form homogeneous mixtures. And that is the reason why zirconium abundant. Zirconium is very much abundant and hafnium rare. And this is found out as impurity. In zirconium, hafnium is actually found out as impurity in zirconium. And it is found around 130 years later. You must understand. So people are mining hafnium outside, but I think it was actually as an impurity in what? Zirconium, you must understand here. So zirconium and hafnium have similar radii, and each one is in the impurity in the other. Because of this, you must understand that. Right? So when the sizes are same, even I can simply say the Zr plus 3 and hafnium plus 3 have similar polarizing powers. They have similar polarizing powers. and they have same basic nature. They have same covalent nature, and everything will be similar, and all the properties which are dependent upon ionic size would be same for zirconium and hafnium. That is one direct consequence of having zirconium and hafnium as a direct consequence of what? Lanthanoid contraction. What the first consequence for people who are writing their exams, especially advanced exam, the theoretical question will be, what are the consequences of lanthanoid contraction? Then you have to say zirconium and hafnium have similar radii. Whether it's a ionic radii or other radii in picometers, if you actually see, they have similar radii. When you have similar radii, you have similar polarizing powers. Same basic nature. Same what? Covalent nature. And all the properties that are functions of atomic radii would be same for zirconium and hafnium. You don't need to take it individually. Right? Whether it is solvation energies, whether it is complex forming tendencies, basic natures, or even polarizing powers, all would be same for zirconium and hafnium, and that is because of lanthanoid contraction direct consequence. You must understand. That is the first. If I go for the second consequence, observe carefully. If you look into the second consequence, consequence 2 of lanthanoid contraction, consequence 2 of lanthanoid contraction, right, look into this, is lattice energies. Now basically what is lattice energy? Lattice energy is nothing but the force. Energy is synonymous to force. So lattice energy is basically nothing but a force that binds ion in a crystal lattice. So it is an average force. It is the average force that exists between ions in a crystal lattice. So it is an average force that exists between ions in a crystal lattice. It's called lattice energy. Average force that exists between the oppositely charged ions in a crystal lattice. If that is the case, then lattice energy is nothing but average force. Then you have Q1, Q2 by RC plus RA. That is nothing but the average force of attraction. Q1, Q2 by RC plus RA. Right? If this is the case, then since we are speaking of lanthanides, let us focus on cations. So I can simply say lattice energy inversely related to radius of cation, provided Q1, Q2 are same and RA is also what? Same. If this is same, this is same, this is same, then if there is a situation where you have to judge on the basis of cations. For example, if you look into this, if you actually wanted to compare lanthanum hydroxide lattice energy with lutetium lattice energy, if you wanted to compare lattice energies of these, right? So what is Q1, Q2? If I write Q1, Q2, lanthanum is plus 3. So 3 into 3 minus, OH minus, you have a minus charge over there. So 3 into minus 1 is minus 3. So 3 into 3 will be 9. And for this also 3 into 3, which is 9. So Q1, Q2 is basically same. Basically same. Right? And radius of anion we need not consider, because of radius of anion is both, it is OH minus in both the cases. So there is basically nothing. Radius of anion is same. The only variable thing is the radius of cation, that is lutetium and what? Lanthanum. So in such cases where Q1, Q2 is same, and the radius of anion is also same, then if you are stuck how to judge lattice energies on basis of radius of cations, then it's inversely relation. You must understand. So try and understand what I'm telling clearly. Clearly, the lattice energy expression is like this. It is basically an average force. Observe, lattice energy is nothing but average force, which is given by the expression of the product of charges, that is cation and what? Anion, cation and anion, and divided by Rc plus Ra, that is radius of cation plus radius of anion. Suppose Q1, Q2 is the same and Ra is also what? Same. Then lattice energy is judged on the basis of radius of cation. You must understand this. Lattice energy is judged on the basis of radius of cations, and cations are formed by lanthanides. You must understand. And what we observe, if this is the case, in lanthanides, that is from lanthanum to lutetium, contraction occurs. There is contraction in size. That's what we are discussing. That's lanthanoid contraction. If there is decrease in size, then you can say, then the size of lanthanum plus 3 is greater than lutetium plus 3. You must understand that. You must understand that. If this is the size, then lattice energy is inversely related to the size of cation, radius of cation. Then the lattice energies trend of La plus 3 is actually inversely related. So you must understand this is inverse relation. Right, this is the size. So lattice energy of La plus 3 is less than the lattice energy of this one. You must understand this. So simply speaking, the lattice energy of lanthanum hydroxide, trihydroxide, if you check it, then since this is bigger, I think it will be lesser compared to what? The lattice energy of lutetium hydroxide. You must understand this, right? So lattice energy trend is also important for students who are writing their JEE advanced exam for IIT, right? And I would like to explain this again and spend some time again here. If someone is asking you what is lattice energy, then it is nothing but the average force of attraction. It is the average force of attraction that exists between oppositely charged ions in a lattice. If that is the case, then it is given by Coulomb's law, which is Q1, Q2, which is the product of cation charge into anionic charge divided by distance between charges, that is nothing but Rc plus Ra. If you say this is same and this is same, then the lattice energy is inversely related to radius of cation, and in lanthanides the size goes on decreasing. So lattice energy is basically what? Of lanthanide plus 3 will be lesser than this, because this will be having the smaller size. And that's what I have given for hydroxides. If you see Q1, Q2 is same, and radius of anion is also same, because the anion is nothing but hydroxide. So the lattice energy of lanthanum hydroxide would be lesser compared to what? The lattice energy of lutetium hydroxide, because lutetium is smaller in size, lattice energy would be more. You must understand that, right? So inversely related to what? Radius of cation. So smaller the cation, more is lattice energy. So I think we have done it reverse here. Just a small correction, please. Watch carefully here. Small correction. Well, the size of lanthanum plus 3 is greater than this, and lattice energy is inversely related to size. So the lattice energy of all the crystals La plus 3 would be smaller compared to what? Lutetium plus 3, right? It's an inverse relation. Lattice energy is inversely related to what? Size. So the lattice energy of lutetium hydroxide would be greater compared to what? Lanthanum plus 3, you must understand. That is the second direct consequence. So if you can go for the third, then it is somewhat like this. Watch carefully here. So if I can recollect, the first one, zirconium, hafnium, zirconium having similar ionic radii, right? That is the first. Then I can simply say lattice energy, right, will be increasing in lanthanides from lanthanum to lutetium. You must understand. Lattice energy is increasing in what? Lanthanides from lanthanum to lutetium. Because the size is decreasing, then the lattice energy would be increasing. And the reason for that is lattice energy inversely related to what? Size. So as the size is decreasing, the lattice energy is increasing as size decreases. Right? That is one. Then if you look into the third consequence of this, hardness increases in lanthanides. Lanthanides as size decreases. So if you look into the hardness trend, hardness, I think it will be decreasing from what? Lanthanum to what? Lutetium. Because the size decreases, then the density will like to increase, right? And the hardness also what? Increases with what? Density. So if you look into the hardness, it is increasing. It is hardness basically increases from lanthanum to lutetium. Hardness increases, right? So lanthanum is less harder compared to what? Lutetium, you must understand. Lanthanum is less harder compared to what? Lutetium. As the size is decreasing, density is increasing, and hardness is also what? Increasing. So you can actually see lutetium is much harder compared to what? Lanthanum, you must understand. And then you have density. Density also increases in lanthanides as size decreases. So you can actually see the density trend. Actually lanthanum is less denser compared to what? Lutetium. Because of what? The increase in what? Hardness. So as hardness increases, or otherwise as density increases, hardness would be increasing. Look into the melting point trend. Melting points trend. And remember, this also increases as size decreases in lanthanum. So the melting point of lanthanum to lutetium, if you actually see, it goes on, right? It goes on what? As the size increases, melting point trend, if you see, density and melting point, both are what? Directly proportional. More density, more is what? Melting point. So you can understand that melting points of lutetium is greater than lanthanum. You must understand. As the size decreases, density decreases, melting point also what? Size decreases, density increases, melting point also what? Increases. So all these are directly related. I can simply say hardness is proportional to density is proportional to the melting points. You must understand. Those are the trends. So for a quick revision, of anyone wanted to have a very quick revision of all the things, then I would like to place them in a box. Observe carefully here, observe carefully. You don't need to write statements. For all those who are preparing, please bank on this. These are 100% sure questions. 100% sure, right? So the size decreases, hardness increases, right? Density increases, melting point increases, lattice energy, as the size is decreasing, the lattice energy will also increase, right? Solvation energies, because lattice energy is inversely related to size, recollect, right? So lattice energy increases. Now what is solvation energy? Smaller the cation, more is solvation energy. So more is solvation energy, that is also increases, because solvation energy will be more for smaller cations. You must understand, I was explaining this. Solvation energy increases, then continuing it, I think basic nature will actually decrease in lanthanides, decrease as size decreases. You must understand, they are directly related. Basic nature decreases, so lanthanum hydroxide is a better base compared to what lutetium hydroxide, you must understand. So decrease, increase, increase, decrease is a confusion which you should be thorough in writing. So the summary of all the lanthanoid contraction are the consequences which I am writing it for you. Just read it again. As the size decreases, hardness increase, density increases, melting points increase, lattice energies increase, solvation energies increase, basic nature decreases. So I can simply say lanthanum trihydroxide is a better base compared to lutetium trihydroxide. That is one. The other one, zirconium, hafnium have similar radii. That is one of the consequence. Right, one of the consequence of lanthanoid contraction. And if you look into the complex forming tendency, which I was explaining, complex forming tendency, that is CFT. Smaller the cation, more will be the complex forming tendency. So the CFT basically increases. So you can expect people, lutetium will be forming more complexes tendency compared to what lanthanum, because lanthanum is having a bigger size. You must understand. Then you have common oxidation states is +3, but you can actually have +4 also, right? You have +4 also for NB, PS, terbium, TR, etc. Around 4 people in lanthanides will also show +4 and +3. That means they are exhibiting what? Variable valency. You must understand, they exhibit what? Variable valency. So if anyone is writing it, write it on a white paper, and just flaunt it and put in your pocket, because these will be asked in the exam. Watch carefully. The consequences of lanthanoid contraction, the gist of what we told is size decreases, hardness increases, density increases, melting point increases, lattice energy increases, solvation energy increases, basic nature decreases, zirconium and hafnium having similar radii, CFT increases, CFT is complex forming tendency increases, common oxidation states are +3, but +4 is also seen in neospedium, prospium, terbium, etc. Some of the elements will also show +4 oxidation state. You must understand that is what is the consequences of lanthanoid contraction. And all these are happening because F subshell is a poor shielder, because it has a peculiar diffused shapes. You must understand that, right?